Welcome. It is finally time to discuss hyperfine splitting, which is the last correction that we have to make to the hydrogen atom. We will also solve problem 6.25 as it appears in the third edition of the book Griffith's Introduction to Quantum Mechanics. Hyperfine splitting is an effect that is analogous to what we saw previously in the case for the spin-orbit coupling, which was this interaction that arose between the coupling of the spin of the electron and the orbit that it was making. Hyperfine splitting, on the other half of the hyperfine term, will come from the interaction between the spin of the proton and of the electron. And the reason it is called hyperfine, as we will see, is because it is actually much smaller than the effects that we saw in the fine structure. All right, so how do we even get to this hyperfine splitting term? How do we work with it? Well, we have to consider the proton in the hydrogen atom is a magnetic dipole, and a magnetic dipole, as we have seen in electromagnetic courses, they generate a magnetic field. So we will have the electron in a magnetic field, and that we know gives us a contribution to the Hamiltonian. So the Hamiltonian from this contribution is going to be Hamiltonian, well, let's call it HF, right? Hyperfine. Well, this is going to be minus the magnetic dipole moment of the electron dot the magnetic field produced by the proton. Now, both of these things, we have already seen this, right? And we even know what the magnetic dipole moment of the electron is. Magnetic dipole moment, oh, that doesn't really look like an E. Let me fix it. This is minus E over M times SE. If you don't know where this came from, you will have to go back to the video about fine structure, particularly the one for spin orbit coupling. Okay, so what is the magnetic field generated by a magnetic dipole moment? Well, this is a formula that I will quote. This comes from electromagnetic theory. I hope you have seen it. If not, depends when you are watching this. I hope that within a few months of making this video, I will be able to work on an entire course on electromagnetism. But either way, this comes from there. Right, mu naught, of course, is a constant for the vacuum, and all of these other mu's are going to be the magnetic dipole moments of the proton. So let's add a p. All right. Now, what is this mu p? What is the magnetic dipole moment of the proton? Well, unfortunately, we can't really do the same procedure that we did for the electron because the proton is a composite structure. It's made out of 3 quarks, and the same procedure just isn't valid. And it was already like questionable before because it was a semi-classical approach. It didn't really consider relativity, and for that reason, it was already kind of not the best approach. But now for proton, it just doesn't work. So we will have to just get the value from literature, and this is G, which is a number 5.59 times E over 2 times the mass of the proton, and maybe let's add an E here to make a difference between both masses, times the spin of the proton. So let's plug everything into our Hamiltonian. So the magnetic field and the magnetic dipole moment for the electron. So the Hamiltonian for the hyperfine structure will be minus this thing. So minus minus will give us plus. So we get E over ME times the spin of the electron times now the magnetic field. So we have 2 terms. Let's multiply by the first one, where we get mu naught over 4 pi r cubed times the term in the bracket, which is 3. And now, well, instead of just the magnetic dipole of the proton, let's actually write it down. So let's write GE over 2 MP spin of the proton dot r hat minus, and again, GE over 2 MP SP. All right, and finally, we still have to consider this last part, which is going to be plus E over mass of the electron, then spin of the electron, then times, maybe just put it, so 2m naught over 3. Let me move this entire thing. And then we get the Okay, now we have to plug in the magnetic dipole moment of the proton. So we plug in GE over 2 mass of the proton, spin of the proton, and then we finally have this delta here. All right, great. So this is the Hamiltonian, and we can still simplify it just a little bit. So the hyperfine Hamiltonian. Now let's see, we can factor out GE and 2MP from this entire first part. So we get mu naught G E squared over 8 pi r cubed, and then the product of the masses, so ME MP. And then we can multiply this spin vector into the square bracket. So let's just plug it in there. So we get 3 times, and then we have this dot product. The dot product will give us a scalar, so we can just commute it with the SE vector. So that means that we can just write the vector afterwards and write it like this. So SP dot R, SE dot R, right? We simply multiply it through, and we still have this term, so we get minus SR, actually not SR, SE dot SP. Okay, and this final part, we get mu naught GE squared, the 2 cancel out with the other one, mu 0 GE naught, then we divide by 3, ME, MP, what else? So we already included this, then we have the dot product, SE, SP, and delta cubed. Okay, so this is the Hamiltonian that we have to work with. So if we now want to find the energy levels of the Hamiltonian, actually, let me put it like that. Okay, yeah. There we go. So if we want to find the energy levels of the Hamiltonian, what we have to do is we need to apply the mechanisms of degenerate perturbation theory, because we're dealing with the hydrogen atom, which is highly degenerate. However, as we know, if we can find the good states of this system, then we can work with the mechanisms of non-degenerate perturbation theory, and that would be very, very good. And so let's see if we can figure out what it is. So we have only the spins here. We're only dealing with spin angular momentum. So we could think about dealing only with the quantum numbers of spin, ms and s, and the total spin. So that could be our base, and total angular momentum would indeed be conserved. So that would mean that this would indeed be a good base. So let's use that one. So using the base of spin and total spin, we can find the expectation value of the hyperfine Hamiltonian, which will of course give us the energy of the hyperfine structure. Now, doing that is just applying the, basically taking the expectation value of all that is in here. So let's now write it out. So this divided by 8 pi r cubed ME MP. Then we have, and then just the expectation value of what is inside. So 3. Oh, actually, be careful. This r cubed, of course, we have to take inside, right? The r, of course, you can't just ignore it. You have to take its expectation value. It's not a constant. So we get this SE dot R. Nothing's really changing, so I'm just writing it down again. I just want to make sure we go step by step. R cubed plus mu naught G E squared, and the expectation value of SE dot SP and dr cubed. Okay, so we need to find these two expectation values. So how exactly do we proceed? Let's choose either. So maybe we just say, sure, let's take the one on the left. Actually, I can indeed cover it up. I think that's fine. Maybe just to be sure, let's leave it inside. So let's begin with this expectation value right there. So we can divide it in two terms, right? So the entire thing, let me just go step by step. This entire thing, we can write as the sum of these expectation values, r cubed minus se dot sp that is the same as what we have up here. It's the same thing. And we can even just take this 3 outside, of course, if we want. And maybe we should even do it. All right, so let's just write the 3. Oh, I think that there. Okay, so there you can see it. Actually, it's still not on site. That's weird. Okay, there we go. All right. So this is now what we want to work with. So just choose whatever. Let's begin with the first one. It doesn't matter which one you go for first. And we want to find the expectation value of this. Now, the question is, of course, the expectation value in which state. To find it generally, right, for any state, that's just not really something you could do without an incredible amount of trouble. So let's decide on some state. Let's say, for example, the ground state, 1, 0, 0. In this case, of course, the state will only depend on R. Right, the spherical harmonic here, this is simply some constant. I think it's like 1 over square root of 4 pi or something like that. So it doesn't depend on theta or phi. So let's write this expectation value explicitly. So I'm thinking what to call it, but maybe let's just write it down and we will know what we are talking about. So only the expectation value without the 3, right? That would be integral over from 0 to infinity, from 0 to pi, and from 0 to 2 pi. And then we have, of course, the wave function, the conjugate of the wave function, sp dot r, r hat, not r vector, r hat, se dot r hat, and divided by r cubed times now r squared, because we are integrating in spherical coordinates, sine of theta, this is phi, so the phi, the theta, the r. So that is what we want to integrate. Now notice, oh, I'm missing there's one thing I'm missing. Maybe let's move this. There we go. I'm missing the other wave function. So we want to integrate this. So let's separate the things that depend on R and those that don't. So the wave functions, of course, both depend on R. We can just commute them. These things right there are just quantities. They're just some numbers. It's not a problem. So we get the modulus squared of the wave function divided by R dr. Nothing else depends on R. This r hat does not depend on R either. It might look confusing, but that's just a constant vector, so it doesn't depend on R. And then we still have integral from 0 to pi, from 0 to 2 pi, and then we have sp dot r hat and se dot r hat. And of course, sine theta, d phi, d theta. And this is exactly the starting point of Griffith's problem 6.25. So let me go find it. Here we go. So Griffith's problem 6.25. Here we have it. So it says, let a and b be two constant vectors. Show that this integral right here, which we just found, except that a was, I think, sp and b was se, right? The two vectors for spin. We want to show that it is 4 pi over 3 and then the dot product of A dot B. And we have to integrate over 0 to pi and 0 to pi. That's what we're doing. And we want to use that to demonstrate that this expression, which we just came across, right? Remember this, that is, let me find it. This thing right here, right? We want to show that this right there is 0. So that is what we want to do. So, and this is valid only for states with L equals 0. But we are working with the ground state. And of course, that is the case. And why is it only for L equals 0? Because when L equals 0, then the wave function is only it only depends on r. It doesn't depend on either theta or phi. So we can do all that we are doing right now. Otherwise, we will be in trouble. All right. So we want to solve this integral. Let's write it out explicitly. So what is A? Now, A is, of course, our equivalent for SP or SE. Doesn't really matter. It's the same thing. But it's going to be a three-dimensional vector, right? The spin has Sx, Sy, and Sz. So A will be a three-dimensional vector with an X component, with a Y component, and with a Z component. And B will be similar, of course. It will have an X, a Y, and a Z component. Now, then what is our R vector? That is actually written here. Oh, almost closed it too early. And the integral we already know. We know the integral goes from 0 to pi and 0 to 2 pi. So let's now write this parenthesis, the multiplication. Let's write it out explicitly. So that's going to be A dot R. So we get AX times the X part of the R hat vector. So AX sine theta cosine phi. Okay. Plus AY times the Y part. So we get AY sine theta sine phi. And then we get AZ times the Z part of the R hat vector, which is simply cosine of theta. And then we get B dot R, which is going to be exactly the same thing, except that instead of having AX and AY and AZ, we have BX, BY, BZ. So we get BX sine of theta cosine of phi plus BY. Maybe let's zoom out just a little bit. I'm not sure if I have enough room if I don't. Okay, so BY sine theta, whoops, sine, not cosine, sine phi, and finally plus BZ cosine theta. And I actually need a little bit more room. So then we have sine of theta d phi d theta. All right. So as you can see, this integral is not particularly small. It isn't particularly pleasant. So maybe let's find some way to simplify it. Because of course, multiplying each one of these elements through and then seeing how we can integrate is kind of annoying. But what we have to notice here that, well, we have basically the same two expressions. So AX, BX, all of them are just constants. So the things that we actually integrate, they are the same. So we have sine theta cosine phi here and sine theta cosine phi, right? And they kind of repeat. So if we were to multiply, for example, the first with the first, we get sine squared times another sine, and then cosine phi squared, all right, which it's going to give us something, but it isn't particularly interesting for now. So maybe let's see the other terms, because we are looking and hoping that maybe something will cancel out, something will be 0. So let's now go for AX times the BY part. So AX times this. When we do that, we will get sine theta cubed again, and then cosine phi sine phi. And that might ring a bell. So if we are integrating from 0 to 2 pi, sine theta times cosine, not theta, phi, sorry. Sine phi cosine phi. Now this might ring a bell. If it doesn't, don't worry. I'm going to walk you through it. So let's just integrate this. So what we get here, we can just rewrite this as sine of 2 times phi. So sine of 2 times phi divided by 2, and of course d phi. And this would be minus cosine of 2 phi over 4 evaluated between 0 and 2 pi. And cosine of 4 pi, so minus 1/4, cosine of 4 pi is 1, cosine of 0 is also 1. So this thing is 0. So if we multiply ax, the ax part times the by part, we get 0. And because of the fact that these two expressions are the same, if you multiply bx times ay, we also get 0 because it's going to be the same thing. It's also going to have sine phi, cosine phi, except that the constants will be different in front, but it doesn't matter. Any constant times 0 is 0, no problem. All right. So we have now looked at ax, ay. What about ax, az? So that's the next one. So ax times bz, bz. So if we do that, we get sine theta squared, and then we get cosine phi. And that's another red flag. And then cosine theta, but that's not too interesting. But we get integral from 0 to 2 pi of cosine of 2 pi. Not of 2 pi, sorry. Cosine phi. And of course d phi. But this is simply sine of phi between 0 and 2 pi, which is 0 minus 0. So super 0, right? So ax times bz is also 0. And then if we go to the next one, ay times bx will be 0 again, right? We already discussed that. And then we would have ay times by. That would be the next term involved. So ay times by, we would get sine theta squared cubed, and then sine phi squared. Similar to what we had in ax bx, it doesn't really seem like any of that is going to be 0. Maybe it will, but at least at first glance, I don't see how that could be. So let's continue. Then we would have the ay times bz. In that case, we have sine theta squared times cosine theta, and then we have integral. We have the sine phi, so that would be integral from 0 to 2 pi of sine phi d phi, which again, you might already know is 0. If not, don't worry, you can integrate it and see immediately that this integral is also 0, right? It's going to be minus 1 minus 1, which is 0. So the ay bz part is also 0. And finally, az bx is 0 for the same reason that ax bz was 0, right? It's the same. The theta and phi parts are the same, only the constants changed. The az-by part is 0 for the same reason that the ay-bz part was 0. And the only part that is not 0 is going to be the az-bz. Okay, so that was a mouthful. But what this told us is that most of these parts are actually going to be 0. Let me now get rid of this. Wait, what am I doing? I left most of it out. All right. Okay, so let's now write only the parts that will not be 0. So we will have to integrate from 0 to pi, from 0 to 2 pi, the ax bx part, which will be sine cubed of theta, and then cosine squared of phi, the phi d theta. And then we will have another integral over the same range, of course. I'm just separating them, and that will be ay by, and then we have sine cubed again, sine cubed of theta, times, this time it's going to be sine squared of phi, d phi d theta. And finally, we have integral from 0 to pi, 0 to 2 pi, az bz, and this time it's going to be cosine squared of theta, sine of theta, d phi d theta. Okay, so we want to now solve these three integrals. So of course, let's begin with the first one. And we can actually see that there's two parts to it. So of course, we can separate this into the phi and the theta part. So maybe let's call it I1. And let's see. So I1 this will be the phi integral will go from, the theta, this is the theta part, we go from 0 to pi, and we will have sine cubed of theta and nothing else, so d theta. And then we have 0 to 2 pi of cosine squared of phi d phi. And of course our constants. So we have these two integrals to solve. So maybe let's call them 1, 1 and 1, 2. Not very creative. So 1, 1. And this will be 1, I, 1, 2. So let's go for I1, 1 first. So I1, 1, this is integral from 0 to pi of sine cubed theta d theta. So how do we solve this integral? Well, at first glance, maybe we don't know, but we do know how to work when we have sines and sine squared. So let's rewrite the sine cube, which maybe we don't know how to work with, as sine theta times sine squared theta. And sine squared, we know that we can write it in two different forms, at least. Sine theta, we can write it as 1 minus cosine of 2 theta. Is it minus or plus? Maybe I should double check. I'm going to double check real quickly. So we know that we can derive it if we have 1 is equal to cosine squared of theta plus sine squared of theta. And we also know that cosine of, not squared, but of 2 theta is cosine squared minus sine squared theta. So we can add these two together, and we have 1 plus, actually no, we have to subtract them if we want to find the formula for this one. So we have to subtract them. So if we subtract them, we get 1 minus cosine of 2 theta. This is equal to 2 sine. Okay, so it was correct. Okay, never mind. I doubted myself for no reason. Oh, I did not intend to do that. Okay, so I doubted myself for no good reason. Okay, so this is one way to rewrite it. And the other way is to write it as 1 minus cosine squared of theta. So those are the two ways. You could try either, but the thing is that if we were to plug this in, then we would get one term that is sine theta times cosine of 2 theta, and at least I wouldn't know how to integrate that right away. And on the other hand, if we use this, we will get one part, this one, which would be sine of theta, and this time, this one will be sine times cosine squared, and we know how to solve that by substitution. That's why I will use this. So now we plug that in, so we get sine of theta times 1 minus cosine squared of theta d theta. All right. And now we just multiply through, so we get two integrals, 0 to pi of sine theta d theta. And then we have minus integral from 0 to pi of sine theta cosine squared theta d theta. So the first one we can solve immediately. The second one will require substitution. So what substitution do we use? Well, the easiest thing to do is say, okay, u is going to be cosine of theta, and du will be the derivative of this, so minus sine of theta d theta. So let's plug all of this in and solve this. So integral of sine will be minus cosine theta, and we have to evaluate it between 0 and pi. And then we have this other part. Now, du will be minus sine theta d theta, so this minus sign will be absorbed, so we get plus. And then we have integral from the lower bound, which is when theta is 0, so we get 1. And the upper bound is when theta is pi, so it's going to be 1. And then, well, sine theta went into the du, and we get u squared du. Okay, so next step, this part right here is going to be minus minus 1, minus 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 1. So basically, we're going to get 1 plus 1, right? So minus minus 1, and then minus minus 1. There we go. I think I said it wrong the first time. So we get 2, basically. And then we have this other integral, which will be u cubed over 3, evaluated between 1 and minus 1. And that's going to be 2 minus 1 minus 1 over 3. Actually, maybe plus this. So because u at -1 is -1, and I mean u cubed, and it's 1 minus 1 at both places. We get 2 minus 2/3, which is going to be 4/3, right? It's 6/3 minus 2/3, that's 4/3. Okay, so that is 1, 1. What is the integral 1, 2? Now it is that one, just so that you remember. So I1, 2, what was it? So let me move a little bit to the side, there we go. So I1, 2, this was the integral from 0 to 2 pi of, I think it was cosine squared, but I need to, of phi. Okay, let me, there we go. D phi, let me double check. Yes, it was cosine squared. Okay, that's great. So here it's going to be a lot faster. Let's just write, instead of cosine squared, let's use 1 minus, actually plus, I think, cosine of 2 phi. Let me double check that it is indeed plus. Yeah, it would be plus, yes. D phi. So we integrate this. The first part, the 1/2, would give us 2 pi over 2. And then we have integral from 0 to 2 pi of cosine of 2 phi, which is 0. As we have seen before, you can just integrate it and you will get, again, 1 minus 1, which will be 0. So basically, this integral is simply pi. So the integral I1, which was the product of these two, is simply going to be 4/3 times pi. All right, so that is the first one. What about the second integral that we have right here? Now, as you can see, this will have the sine cubed part, which is the same integral that we just did, and that was 4/3 times pi. Sorry, only 4/3, not a pi. And then we have the integral in phi, which has sine squared. And the thing is that if we integrate the sine, what did I just do? If we integrate the sine squared part, right, so in the second integral, we would get integral from 0 to 2 pi sine squared phi d phi, which we can write as integral from 0 to 2 pi 1 minus cosine of 2 phi over 2 d phi. But this part is still 0. It doesn't matter if it has a plus or a minus in front. So that is still 0. So this integral is still pi. So going back up, we would know that this part is pi. So the product is still 4 pi/3. So what about the last integral? This one right here. This one has cosine squared theta sine theta. Right, so maybe let's go through it just to make sure that we get it right. So the last integral, I3, is integral from 0 to 2 pi, from 0 to pi of sine of theta times cosine squared of theta d theta d phi. So the phi integral we can solve immediately. It's simply going to be 2 pi, right? There's nothing to integrate there. It's just 1. And then we have sine theta cosine squared. But that is an integral that we already solved. If we go back a little bit, it should be here. There it is. It's right there. So what was that result? It was minus 2. Actually, it was plus 2/3 because the minus sign was already outside, I believe. Yes. So it is 2/3. Oh, what have I just done? So we now have to multiply this by 2/3. So we get 4 pi over 3, right? Thankfully, most of these integrals were basically the same, so we didn't have to worry too much about it. So now if we go back to this huge integral, we can see that if this part here was 4 pi over 3, and now times ax bx, this part right here is 4 pi over 3 times ay by, and this part is 4 pi over 3 times az bz. So basically, that entire integral is simply going to be 4 pi over 3 factor of ax bx plus ay by plus az bz, which is the same as the dot product between the a and b vectors. And with that, we have now proven or shown, right, this first part. So we have shown that this integral has that value. And now we want to apply that to our case, right? We are going now back to Hyperfine, to the Hyperfine case, and we want to show that this expression that we found previously is going to be 0. So let's go do that. Okay, so let's now go back to the expression that we had before. So we had left off kind of about here, and we had seen that, well, if we separate the radial part, right, so we make this integral from 0 to infinity, where we would get the absolute value squared of the wave function divided by r dr, then the rest would be exactly the same integral that we just solved, which we now know is 4 pi over 3 times the dot product of the two vectors, which are sp and se. So that is this first part, right? We know that that is this, up until the minus sign. Okay, and we haven't included the 3 yet, so let's actually multiply all this by 3. And now let's plug in the rest. So let's plug in this minus expectation value of se dot sp over r cubed. Because that is the expression that we want to find. And just a quick reminder, why do we want to find that? That is because we are finding the energy here, and we want to find this part and still this second part there. All right, so let's work this out. Now, the first part here, we don't really need to do particularly much for now. Let's work on the second part. So let me copy this and move it. Okay. Now this, let's write it out explicitly as we did before. So it's an expectation value. So let's write it out as the integral from 0 to infinity, from 0 to pi, from 0 to 2 pi, and then the things that are inside. So the wave function conjugate, se dot sp over r cubed, the wave function again, r squared sine of theta, and then the phi, the theta, dr. Okay, and now notice that there are actually a few very nice things. So these se and sp, these vectors don't depend on theta, on r, on phi, on nothing. We can actually just take them out of the integral. And another nice thing is that, once again, since we're dealing with states where L equals 0, in this case the ground state, but this applies to any state with L equals 0, the wave functions do not depend on theta or phi, because the spherical harmonic is 1 over square root of 4 pi, which doesn't depend on theta or phi. So it strictly depends on r. For that reason, we can separate it just as we did here. So writing now the next part, we can actually, by the way, simplify these two. We get integral from 0 to infinity, psi squared over r dr times 4 pi sp dot se minus, and now let's factor out the dot product. So sp dot se, I turned it around, it doesn't matter. Integral from 0 to infinity of psi squared over r dr, and then we get integral from 0 to pi. That's the way I wrote it before. So 0 to pi, that is theta. So here we would get sine of theta, the theta, and then integral from 0 to 2 pi of the phi. Okay, now we can notice that we can actually factor some things, which would be very nice. So we can factor out the integral, for example. So integral from 0 to infinity, what kind of an infinity is that? From 0 to infinity, psi squared r dr, and then we can actually even factor out, by the way, the dot product here. So we can factor out sp dot se, and then we get from this first term 4 pi, and then minus these integrals. But what are the integrals? Well, this one is easy. It's simply 2 pi. So we get at 2 pi. And this one, it's going to be, well, it's going to be cosine, or rather minus cosine. So we get plus here, cosine of theta evaluated between 0 and pi. Now, what is that? So cosine of pi, so that this is 2 pi times cosine of pi is minus 1 minus cosine of 0, which is 1. So we get minus 2. So in here, we get 4 pi minus 4 pi. So we get that this entire thing is 0, which is exactly what Griffiths, the problem in Griffiths asked us to solve. So going back, we have now seen that that expectation value is indeed 0. So if you're here for Griffiths' problem, that was it. So all we did was solve this integral, which was kind of annoying, and then plug it in. Right? Something important that we have done a few times, though, is writing out the expectation value explicitly so that we can separate which parts depend on r, which parts depend on theta. But now that we know that that is 0, we can actually go back just a little bit, or maybe more than a little bit, to this formula right here, which was the energy for the hyperfine structure. And we now know that this entire first part is 0. So this entire thing, well, okay, not that much. Okay, wait, why doesn't, okay, never mind. I'm just gonna, I don't know why I can't Control Z that, but I guess it doesn't matter. Okay, so this entire thing is simply what we have there, which is mu naught g e squared over 3 me mp, and then the expectation value of all of these things. All right, so how do we do this now? Let me maybe get rid of a few things here. So how exactly do we continue? Well, now we need to find that expectation value. Okay, maybe just give me a second. I'm gonna just delete all of this. I want some space. Okay, so we want to find that expectation value right there. How do we do that? Well, as we have done this entire video, let's write it out explicitly. So integral from 0 to infinity, integral from 0 to 2 pi. I kind of flipped them, but it doesn't matter. 0 to pi. And then we get psi conjugate, then SE dot SP, and then the, oh, sorry, we're not in quantum field theory, d cubed r. And then again, psi r squared sine theta. Okay. And of course, the theta, d phi, dr. So once again, as we have done, let's separate this between the things that depend on r and those that don't. So the r integral will have, again, our wave function squared. Oh, sorry, this time there is no divided by r cubed, my bad. And then we have the delta function and dr, right? Yeah. Okay, and then we have the rest of our stuff. So we got integral from 0 to 2 pi, integral from 0 to pi. And actually, maybe I should, in a second, I'm gonna delete the thing that is here so that it doesn't bother us. I should have given it more space. This is my first time using this software, so I haven't gotten used to it yet. Okay. 0 to pi, what else? Then SE dot SP sine of theta d theta d phi. So basically, what we have here is that we have two expectation values, if we think about it. Because this part right here does not depend on r. So if we were taking, we could add the integral of our normalized wave function, r squared dr. This thing is 1, right? Because it's normalized. And if we were to add that here, by add I mean multiply, not like mathematically add, then this entire thing here would simply be the expectation value of SE dot SP, right? So this is perfectly legal. There's nothing wrong with this. And I'm going to repeat it. So now that we got rid of the annoying delta that was in there, this is simply the expectation value of this. And we can now go to this part and do exactly the same thing. So if you were here to multiply by the integral from 0 to pi, from 0 to 2 pi of sine theta d phi d theta, this thing is 1 because it is normalized. So what you would have here then would be the expectation value of your wave function. But in this case, it's going to be the wave function evaluated at 0, of course, because of the fact that you have this delta function here. So this would be, let's see, so this right here would end up being your wave function squared, but evaluated at 0 because of your delta function, right? It breaks your integral. So this part right here is simply 1, and this part right here is simply going to be the wave function squared evaluated at 0. Okay, so this is what we end up with. All right, we end up with this right here. Okay. Now, what do we do with this? We now need to find this expectation value. So, oh wait, oh my God, what pen did I just, what? Okay, so the expectation value of SE.SP. Now we have done things similar to this in the past, and the way to go about it is say, all right, well, let's consider the vector S, which is going to be the sum of SE and SP. And if we square it, then we would have SE squared plus 2 times SE SP plus SP squared. So from here, we can immediately see, as we have done in the past, but for angular momentum, we see that SESP is going to be S squared minus SE squared minus SP squared divided by 2. So we can now plug this into our expectation value, and we will now have the expectation value of S squared minus SE squared minus SP squared over 2. And this is now much, much, much easier because we are in states of spin, where spin are eigenfunctions, eigenvalues. So for that reason, we simply apply what we know from spin angular momentum. So we know that S squared acting on its eigenfunctions will give us h bar S times S plus 1. And the same for this part. This would be minus, oh sorry, h bar squared, by the way, h bar squared SE, the spin of the electron, SE plus 1. And for the proton, it's the same. So SP plus 1, and all of this divided by 2. We can now just factor out h bar squared over 2, and the end result will be S plus 1 minus 3 over 4 minus 3 over 4. So if we add both of them together, that's simply minus 3 halves. So what is the total spin? So the total spin can, if they are parallel, it's going to be 1, right? If the spin of the electron and proton are parallel, it's going to be 1/2 plus 1/2, 1. And if it's anti-parallel, they're going to subtract, and it's going to be 0. So S can be either 0 or 1. If it is 0, then this thing right here will be h bar over 2 times this minus 3 halves. So minus this times 3 halves, so minus 3 h bar squared over 4. And if it is 1, then we will have h bar squared over 2 times 2 minus 3 halves, which would be 4 minus 3, which is 1. So we would get h bar squared over 4. So these are our two possible values for the expectation value. of this thing right here, which is of course the same as this thing right here, which is what we now want to plug in to this part right here. We now have to just go back a lot. That's the point here. So we have to go back here. So this is mu naught g e squared over 3 mass of the electron, mass of the proton, times the wave function of the ground state evaluated at r equals 0 squared. Okay. And then we still have the expectation values. Maybe let's write it like the expectation value. And now we will just go somewhere where we have more room, so we don't have to worry about anything. So let's copy it. And now let's just go way down. So somewhere over here. Wait, I can't go any further down than that. Wait, okay, never mind. So we'll just go there. Okay. So the energy levels due to hyperfine structure, it's going to be this. And now let's write this out explicitly. So this is either going to be h bar squared over 4 or minus 3h bar squared over 4. And what is this energy here, or what is this wave function? So psi 110, let me see, I wrote it down here. That is 1 over pi a cubed. So that means that the energy for the hyperfine structure, let's see, we can factor out the 4 if we want, the h bar squared. So we will get mu naught g e squared over 4 pi a cubed me mp. And then maybe you could also leave the 3 here actually, well, times 3. And then we have, of course, the two possibilities, either 1 or minus 3. So these are the two possibilities for energy. And this is what we call the hyperfine splitting. This is the spin splitting, right? Because this arises from the interaction between the spin of the electron and the spin of the proton. And as you can see, it either rises the energy by 1 unit of mu naught g e squared over blah, 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 or it raises it by 3 times this amount. And that is hyperfine. Now, you could do the same procedure for any level. Levels with L equals 0 are very easy. If you start climbing, it's gonna get increasingly difficult. You would have to know the exact wave function, and it would be quite annoying. But this is the way you go about it. If you had anything where L is not 0, as I mentioned, you would just have to go do the integrals, and yeah, it wouldn't be particularly fun. But well, I hope this video was useful. If that was the case, make sure to leave a like on the video, subscribe if you haven't already. It doesn't cost you anything, but it really helps me out a lot. I'll see you in the next video. Thank you very much for watching.